Hi, my name's Makenna, and I am a junior student at Lawrence Tech University, and I am studying both biomedical and mechanical engineering, and I am a member of Totally Tubular, and this is our final design expo. So I will be focusing on the customer focus and creating value portion of our presentation. So in the beginning, we needed to define our customer, and we learned that we would be building a product for Eileen and the members of Connect Us. So to better understand our customers, we began to research and look into our customer pains. And we specifically throughout the summer, we defined two pains that we focused on when building our product. The first pain that we identified was making sure that our customers were able to get enjoyment out of the design. We recognized that there was often visual challenges that our customers faced, and we needed to make sure that our design was enjoyable for our customer. And to do this, we made sure that our design was colorful and would be fun to use, so we painted our design both red and yellow. Second, we looked into how people with disabilities such as cerebral palsy might experience pain when completing tasks. So we wanted to make sure that when using our product, the customers would be able to complete the task with little to no pain. We did this by adding a button that the user could simply press to make the process virtually painless. So after we just identified the customer's pains, we needed to create value for Eileen and Connect Us. And we did this by selecting the design that was on Eileen's wish list. It is not something that she has had prior. So after determining we would be making the chapstick dispenser, we then analyzed the customer's needs and then used those needs to determine the design requirements. Our customer needs were that we needed to create a design that would be both entertaining and engaging and would also need to accomplish our goals that we set in our target specifications. We split the design requirements into three categories, which were must do, might do, and must not do. And we got these from our customer needs. We then followed these design requirements and used them when we were both creating our prototypes and our final design. Our design theme is stated as accessibility in service to others, and on the left I have included a graph that shows the percentage of children with cerebral palsy who experience pain when doing certain movements.
Hi, I'm Jared Baxter. I'm a sophomore at Lawrence Tech, and I am studying to be a mechanical engineer. Today I'll be talking about the market research, the ideation, and the concept selection that was done to create the final product for our group. So to start off with, we created a must-do, a might-do, and a must-not-do list. This was to determine what we wanted the system to be able to do, what might be able to be done to make it more customer-friendly, and a must-not-do list obviously determines what must not be done by the system once it's finally completed. The concept generation worksheet helped us to generate a lot of concepts that we thought might help us and might be good to use on a final design. It also helped us design the two prototypes, which you will see later. A list of the concepts can kind of be assembled in the picture on the right hand side of the screen on the bottom. For the market research, we looked into the patents that have been done in similar areas in general times in the past. This allowed us to see if there was anything that might be helpful to us and that we might be able to use or adjust to help with our product. The brainwriting activity helped us to determine what concepts from the concept generation worksheet were going to be feasible by talking about them with other groups in the class. And this allowed us to remove some concepts if we thought they wouldn't work, or add some if somebody else came up with one that seemed to work really well, or we thought would be able to. The horrible ideas activity eliminated the worst options that were possible because everybody in the class gave their worst options that they could think of, and this helped to narrow down our focus on the best concepts that were available, and that can be seen a little bit below. You don't see any ideas like setting a chapstick on fire to make it more entertaining for the kids as you look at the concepts seen below. The concept selection matrix was probably one of the most useful tools that we used this semester while designing this product. It was used to rank certain concepts based on the criteria that we came up with a team, and we used cost, development time, pieces required, length of cycle, assembly time, setup time, and the weight. Ultimately, this left us with our two best options that we had, and that was using a button or a lever to activate the system, and it was also using the design of a straw dispenser, and that was kind of first thought of after the patent research. This just means that we stacked the chapsticks up in a line, and then one by one they would slowly get dispensed out. I think the concept selection matrix really helped us because it made us take a big picture view of everything that we were doing, and it made us look towards the final goal of what was going to be possible, what might be possible, and what definitely was not possible based on what we wanted the system to be able to do.
The product architecture can be seen in the CAD drawing on the slide. This drawing is measured in inches. The important parts of our system are the dispenser, ramps, and button. The button is an easy-to-press way to start the system, so all the students can do it. The dispenser holds 20 to 40 chapsticks, and when the button is pressed, distributes one chapstick onto the ramps. The ramps then guide the chapstick into the bucket at the end. The inclusion of the ease of use will allow everyone to have a fun time at our station. As for the product development economics, the customer said with the inclusion of the button and motor in our system, she would pay $175 for this design. We aimed for a target cost of $140, so we would be well under the price the customer would pay. We ended with a BOM cost of $98.07, which is well within our target cost. This looks good for us because it would mean we could make a fair profit of $42 off of materials alone, so money made will be high as long as we keep our labor costs low. Unfortunately, with the research and development for the first design, labor costs were high, but in the future, buildings of it will be cost much lower. However, with the high labor costs, we would need 227 units sold to break even with this design. This may be a big hurdle, but if the design is well received, then getting recommendations for other places that might need this design would also be easy, allowing for a good chance for us to break even.
Hi, my name is Kaminski. I'm a junior here at Lawrence Tech, and I'm studying mechanical engineering. And I'm here to talk about the highs and lows of our prototyping, customer feedback, and design decisions. At the beginning of our project process, we were assigned on making a prototype of our basic ideas to present to Eileen. We had multiple viable ideas that we wanted to share with Eileen, so we chose to focus on the two shown here. Prototype A shows a ramp and dispenser system. This prototype explores the idea of having a linear track for the chapstick to follow. Unlike Prototype A's linear track, we also explored the possibility of a spiral track for the chapstick to follow. But after discussing both prototypes with Eileen, she warned us that if the chapstick is jammed in Prototype B, that there is no way for her or any of her volunteers to be able to reach in and unjam it. With this insight, we decided to focus on the concepts of Prototype A. This prototype explored the basic ideas that Totally Tubular wanted to include in our final product. As seen, it still includes a 2-ramp system with an overhead dispenser to hold and drop chapsticks. This prototype had very limited function, but the main premise of the project was explored and tested thoroughly. When presenting this prototype, she also gave us some very good insight on the improvement that must be made. She suggested that instead of having the chapstick fall into a bucket underneath the prototype, we should have the ramp extend to the outside of the frame to allow easier collection. Another point that she talked about was the time of cycle. So, we decided to increase the overall size of the product. With all the prototypes done, it was time for the final product. The final product, as seen here, includes a dispenser that holds approximately 40 chapsticks, acrylic ramps and backplate that was suggested by Eileen so that the students could see all the movement of the chapstick, a fully automated push-button system with easily replaceable battery compartment that allows for volunteers to change out batteries if they happen to die within the day, colored PVC tubes that allow for enhanced student engagement, and vinyl tape to limit the friction of the second and third ramp. With all these improvements and innovations that we made to our design, nothing worked. So Totally Tubular had to go back to the drawing board and make some major improvements. I now introduce the new and improved chapstick dispenser. Instead of having 3 straight ramps for the chapstick to follow, we decided to make 2 curved ramps to eliminate the spinning of the chapsticks, which would result in a failure of the station. We relocated the dispenser location to accommodate the new ramp design and also changed the inner mechanism to eliminate jamming. We increased the power supply capability by adding another 9-volt battery in parallel to the first to eliminate voltage drops. We relocated the wire harness to allow for a clean exit for the chapstick. And lastly, the overall effectiveness increased from about 0.001% to approximately 60%.
Hello, I'm Joseph Woytowicz, a transfer at Lawrence Tech this semester, majoring in mechanical engineering, and I'll talk about the target specifications that we based our design upon. Target specifications set bounds for how a prototype or method can perform, or how expensive they are to build or implement. They can include minimums, maximums, ranges, exact or discrete values, or anything else that an engineer can think of to base a design around. Target specifications aren't only set by the design team. Bosses of the team often have a budget or a time frame to complete a project. Even more important than the boss's specs are the customers. They can range from colors to quality to just about anything else that the customer wants. Totally Tubular had 9 specs to base our design around. These were set by our professors, our customer, and the team itself. The instructors for the course gave us limits on cost and component numbers. The cost we had to stay under was $150, and the team met the spec by spending just over $98. We were limited to using 10 components for this device, so when our customer receives the disassembled product, they should find no more than 10 pieces to set up the device. Our customer asked that the product would be lightweight and compact enough to allow easy transport. We set our initial weight goal to 5 pounds, and the final product weighs 10. While this is twice the weight of the goal, it still is not unsafe to hold or carry. The footprint of the device must also be under 42 inches by 24 inches to fit on the station's table. And the footprint of the product is 27.5 by 20.5 inches. The customer also asked us to allow for enough capacity to last a day of working without the need of reloading. 40 was the given number of chapsticks to load, and the dispenser's actual capacity is 20. First and foremost, we wanted a low amount of failures. We aimed high and worked for a 1% failure rate. With limited testing and team building time, we measured 10% success rate. The initial goal would have been a hurdle for the team on campus, but we're happy to achieve partial working conditions under our circumstances. The team also wanted a quick setup time, less than 7 minutes. This isn't just based on the components and how clear it is what goes where, but can also be aided by an easy-to-follow user manual. Again, there was limited testing, and the team measures around 5 minutes. The team also wanted to time how long a user would take to arrive at the station, use the station, take the chapstick, and depart. Unfortunately, we never got to test with an actual Connect Us participant or use equipment at school to stimulate use. Similarly, we aim to keep the station from producing any harmful sounds, but we can never test to verify.
All of us at Totally Tubular would like to thank both Eileen and our professors for giving us the opportunity to help the community and grow as engineers. So from the bottom of our hearts, thank you.